Hi, and welcome back to my Physics Online video lecture series. Today's video, we're going to be talking about some spherical mirrors and some of the equations that may be of interest for these. If you've watched my previous video on the thin lens, then some of these equations will look familiar, and some of them, of course, will be new. As with that video, we need to define for ourselves a few base parameters. And many of them have the same definition as they had, well, at least functionally, as they had for the thin lens. We have the object distance, the image distance, the focal length. I introduce here a radius of curvature, which again is similar to the radius of curvature with the lenses, except that you have only one of them now rather than two, because there's only one surface of interaction. And as before, there's also the lateral magnification, and the heights of the image and the object. So we can kind of specify all of those. As with the lens, so with the mirror, the lateral magnification is defined as the ratio of the image height to the object height. It is also equal to the negative of the distance from the image to the mirror over the distance of the object to the mirror. Now, one difference is that in the case of lenses, a positive value for the image distance means that the image is formed on the opposite side of the lens. So you basically have a situation like this. But for the mirror, you have a mirror somewhere over here. You place your object somewhere, and if you form an image on the same side of the mirror as the object, then that is a positive image distance. A negative image distance means the opposite has occurred. So I guess I could draw that in maybe like yellow or something. If I end up with an image here for the lens, or an image here for the mirror, then this would represent a negative image distance. And that's about all that I can say for that. Maybe just to emphasize that point again, I'll fill these guys in a different color. And so the purple one in both cases represents a positive image distance. The yellow one represents a negative image distance. Okay, so what are some equations of interest besides the magnification for your system? Well, you have on the one hand the relationship between the radius of curvature and the focal length. With the lens, this was complicated because you were doing imaging via refraction, and so the refractive index was present. With mirrors, it's a little bit more straightforward. The radius of curvature is twice the focal length. You're simply making images via reflection. The argument basically goes that if you have a mirror over here, let's say, and it has a radius of curvature centered here, so here would be my R. Now let's imagine that I have a ray incident this way. So it hits just where this radius of curvature line is hitting. So here's my incident ray. Law of reflection says that this angle right here must be equal to the angle of reflection, because this would be my incident and this would be my reflection. But the radial line is normal to the mirror surface, and so my reflected ray basically just passes down here. Now my focal length is essentially where this ray should be crossing through the axis that runs through the center point and this point that we might call the vertex location. And so this right here would be my focal length. So that means that this distance right here is r, this distance right here is f, and you can see that there's roughly 2 f's for an r. A more convincing argument might be to make use of sines and these lengths in terms of the sine of the angles. Essentially, this ends up being true provided that we're using kind of like a very small slice of our sphere. So if we're having to use a big chunk of the sphere, then this starts to break down a little bit and you end up with multiple points that are kind of like the focus. But this right here gets us pretty far. For our purposes of our class, r equals 2f. The other equation of interest is the essentially like mirror imaging equation, and it looks identical to the thin lens imaging equation. 1 over dO plus 1 over di is equal to 1 over f. Since r is 2 over f, f is r over 2, so we could also write this as 2 over r if we wanted to. But by and large, it's the same equation other than that last little bit as what we had with the thin lens equation. The examples that I might work for these basically therefore are pretty similar. We just replace lenses with mirrors. So let's do a quick exam. As our quick example, what we'll do is, let's say you got a mirror. You have your radius of curvature somewhere over here. You've got your focal length somewhere over here. So center is here, focal point is here. Object is basically being placed right here. Okay, so our focal length, and this right here would represent focal length. This right here would represent radius of curvature, which is 48. And this distance right here would represent dO. Notice that all these distances are actually taken from the same point, which is on axis with the center and the focal point where they intersect the mirror. Okay, well, if r is 48, r is equal to 2f, and so f is r over 2, which is 48 centimeters over 2, or 24 centimeters. Now, 1 over dO plus 1 over di is 1 over f, implies that 1 over di is 1 over f minus 1 over dO, and so that is 1 over 24 centimeters minus 1 over 12 centimeters. Now note that 24 is 2 times 12, so this number right here is also the same as 2 over 24 centimeters. So if I have 1 over 24 minus 2 over 24, I end up with negative 1 over 24. So 1 over di is negative 1 over 24 centimeters, and that means that di is negative 24 centimeters. Notice that I've got a negative answer for my image distance. So what does that mean has happened? Well, we can also do the magnification part, which is negative di over dO, and that negative means that I'm going to end up with negative of negative 24 centimeters divided by 12 centimeters, which is just plus 2.0. Okay, now looking back at our little cheat sheet, we just got that the image distance is negative, so the image is kind of like formed in the mirror, so the image is somewhere over here. I'm going to draw it in green just so that it stands out a little bit. Expect our image to be formed basically somewhere over here. And this is just di is negative. It is plus 2, so the plus means that this is upright. So that means that if my original object was an arrow pointing up, then my image is also an arrow pointing up. And then the 2.0 means the image is 2 times height of object. So it's magnified 2 times. Each length scale will be 2 times bigger than the original object. So if my original object is 6 centimeters tall, then my image is now 12 centimeters tall, etc. And that's it. That's basically how we do simple spherical image formation and magnification and so on. So hopefully you've learned something from this brief video, and thanks for watching.